Here are 101 unknown and interesting facts about the earthquake. The word earthquake comes from the Greek terms gaia, meaning earth, and seismos, meaning shake, which together describe the sudden trembling of the Earth's surface due to seismic activity. Earthquakes have been recorded for thousands of years, and the earliest known instrument for detecting them was invented in 132 AD by a Chinese scientist named Zheng. His seismoscope used a series of bronze dragons and balls to indicate the direction of distant quakes, an extraordinary feat of engineering for its time. Even though it couldn't measure magnitude, it accurately recorded the occurrence and direction of quakes from hundreds of miles away. Most people think earthquakes only happen on land, but around 90% of all earthquakes occur in the oceans, especially along mid-ocean ridges and subduction zones. These underwater quakes are often hidden from public attention, but they are extremely important. Many of them generate massive tsunamis that can travel across entire ocean basins. The 2004 Indian Ocean earthquake, which occurred underwater near Sumatra, triggered a tsunami so massive it caused destruction in 14 countries and killed more than 230,000 people. It was one of the deadliest natural disasters in recorded history, showing how submarine earthquakes can have global consequences. Deep beneath our feet, earthquakes don't just happen at the crustal level. They also occur deep within the Earth's mantle at depths exceeding 700 kilometers. These are known as deep-focus earthquakes, and they remain one of the great mysteries in geology. Unlike shallow quakes, which typically cause the most surface damage, deep-focus earthquakes give scientists important clues about the movement of tectonic plates and the behavior of rock under extreme pressure and heat. Understanding them better could improve earthquake forecasting and our grasp of the Earth's internal dynamics. Earthquakes don't only cause buildings to shake, they can completely transform the landscape. In extreme cases, powerful quakes can cause rivers to change course, lakes to form or drain, and even mountains to rise. During the 1950 Chilean earthquake, the strongest ever recorded at magnitude 9.5, large portions of the coastline rose by as much as 10 feet. In Alaska's 1964 quake, entire forests sank below sea level and were eventually flooded by seawater. These geological transformations serve as a reminder that Earth is constantly reshaping itself, often violently and without warning. One of the most eerie phenomena associated with earthquakes is known as earthquake lights, brief, unusual flashes of light that appear in the sky before or during seismic events. Descriptions of these lights go back centuries, but they're so rare and unpredictable that many scientists once dismissed them as folklore. In recent decades, however, photos and videos have confirmed their existence. Theories suggest they may be caused by electrical discharges in certain types of rock under high stress, but research is still ongoing. These strange lights remain one of earthquake science's unsolved mysteries. Earthquakes can cause a ground phenomenon called liquefaction, where soil temporarily loses its strength and acts like a liquid. This usually happens in water-saturated sandy soils and has devastating consequences for buildings and infrastructure. During the 1964 Niigata earthquake in Japan, entire apartment buildings tipped over without collapsing because the ground underneath them turned to mush. Cars, trees, and even people have been swallowed by the earth during such events. The solid ground becomes momentarily unstable and flows like mud. The Ring of Fire, a horseshoe-shaped zone surrounding the Pacific Ocean, is the most seismically active region on Earth. It stretches over 40,000 kilometers and includes countries like Japan, Indonesia, Chile, and the United States West Coast. About 75% of the world's active volcanoes and 90% of all earthquakes occur in this region. The tectonic activity here is due to multiple plates colliding, sliding, and subducting beneath each other. Living along the Ring of Fire means coexisting with a constant risk of devastating earthquakes and volcanic eruptions. Animals have long been believed to sense earthquakes before they happen, often behaving strangely in the hours or days before a quake. Dogs might bark excessively, birds fly erratically, and cats may hide without reason. While anecdotal evidence of this behavior is abundant, scientific research into it has been inconclusive. Some theories suggest animals may be sensitive to changes in electromagnetic fields or vibrations that precede seismic waves, but these hypotheses remain under investigation. Still, many pet owners swear by their animals' uncanny abilities to predict a quake. Earthquakes release a staggering amount of energy, and even moderate quakes can generate forces equivalent to thousands of tons of TNT. A magnitude 7.0 earthquake, for instance, releases about 32 times more energy than a magnitude 6.0 quake. The Richter scale, once commonly used to measure quakes, is logarithmic, meaning that each whole number increase equals a tenfold increase in amplitude and roughly 32 times more energy. This exponential nature explains why even small increases in magnitude lead to significantly more destruction. Seismologists can't currently predict earthquakes with precision, but they are getting better at understanding patterns and risks. Earthquake forecasting involves assessing probabilities over longer periods, such as decades, based on past seismic activity, fault lines, and stress accumulation. One of the most studied faults is the San Andreas Fault in California, which hasn't produced a major quake in the southern section for over 150 years. Experts warn that it's overdue, and efforts are ongoing to prepare for the inevitable big one that could strike Los Angeles or San Francisco. Many people don't realize that the moon and sun can trigger small earthquakes through tidal forces. These earth tides stretch and compress the Earth's crust as gravitational pull shifts. While the effect is generally minor, in areas already under tectonic stress, these tidal forces can act as a final nudge to trigger a quake. Scientists studying earthquake timing have found correlations between quake clusters and lunar cycles, particularly around full and new moons when tidal stresses are highest. During a major earthquake, the ground can move so fast it outpaces the ability of sound to travel through it. These ultra-fast movements can generate a loud, rumbling noise that some survivors describe as a train approaching, a jet engine, or even an explosion. This noise is the sound of the Earth's crust breaking, amplified by underground acoustics and surface echoes. It's one of the most terrifying and unforgettable experiences for those who live through a major quake. The deadliest earthquake in recorded history occurred in Shaanxi, China, in 1556. Known as the Jiaojing earthquake, it had an estimated magnitude of 8.0 and killed approximately 830,000 people. At that time, many people lived in cave dwellings carved into soft cliffs, which collapsed instantly during the quake. The event altered the course of Chinese history and remains a sobering example of how natural disasters can shape civilizations. The 2011 Tohoku earthquake in Japan, which triggered a massive tsunami and the Fukushima nuclear disaster, was so powerful that it shifted the Earth's axis by about 10 centimeters and shortened the length of a day by a few microseconds. The magnitude 9.0 quake was the most powerful ever recorded in Japan, and the tsunami reached heights of up to 40 meters in some places, demolishing entire towns. The combined natural and technological disaster reshaped Japan's approach to nuclear safety and disaster preparedness, creating a legacy of caution and innovation. Not all earthquakes are caused by tectonic movement. Some are induced by human activity. These are known as induced earthquakes and can result from mining, oil extraction, dam reservoirs, or even the injection of wastewater into deep wells. One striking example is Oklahoma, where hydraulic fracking, and wastewater disposal have led to a dramatic rise in earthquake activity. In 2015, Oklahoma had more magnitude 3.0 plus quakes than California. This phenomenon has sparked debate over energy policies and the environmental consequences of subsurface industrial practices. In 1976, the Tanshan earthquake struck northeastern China with a magnitude of 7.5, killing an estimated 242,000 people. What made it even more tragic was that it struck in the middle of the night, catching most people asleep and unprepared. Entire buildings collapsed within seconds, and many rescue operations were hampered by a lack of emergency planning. The government initially suppressed details about the disaster, but it later became a pivotal event in China's approach to emergency management and urban development, leading to stricter construction codes and better earthquake preparedness programs. Earthquake swarms are a lesser-known phenomenon where hundreds or even thousands of small quakes occur in a region over a short period, without one large, main shock. Unlike aftershock sequences, swarms don't follow a clear pattern and can last from days to months. One of the most famous earthquake swarms occurred in Yellowstone National Park, which sits atop a massive volcanic system. These swarms raise concerns about potential volcanic activity, but most do not result in eruptions. They're often a sign of shifting magma or geothermal pressures beneath the surface. Some of the largest earthquakes ever recorded didn't occur on land, but beneath the ocean. These underwater megathrust quakes happen when one tectonic plate is forced beneath another along subduction zones. The resulting pressure release can create earthquakes with magnitudes above 9.0, capable of producing planet-wide effects. The 1960 Valdivia earthquake in Chile, the most powerful ever measured at magnitude 9.5, occurred in this way. The quake generated a tsunami that traveled across the Pacific Ocean, causing deaths and destruction as far away as Hawaii, Japan, and the Philippines. Modern skyscrapers are often designed with earthquakes in mind, using advanced engineering techniques to absorb and dissipate seismic energy. These include base isolators, which allow buildings to move independently of ground motion, and tuned mass dampers, which act like giant pendulums to counteract swaying. Taipei 101 in Taiwan and the Burj Khalifa in Dubai both incorporate such technologies. Ironically, taller buildings are often safer than shorter ones in earthquakes because they're built to higher standards and can better handle ground motion over time. Earthquakes are not just physical events. They can leave long-lasting psychological impacts on survivors. Many people develop post-traumatic stress disorder, PTSD, anxiety, or depression after experiencing a major quake, especially if they've lost homes or loved ones. Nightmares, panic attacks, and a persistent sense of insecurity are common. Mental health support is a crucial but often overlooked part of disaster recovery. In countries like Japan and Chile, where quakes are frequent, therapy and community resilience programs have become integral to long-term recovery efforts. One of the lesser-known hazards of earthquakes is the potential for landslides. In mountainous regions, seismic shaking can destabilize hillsides and cause massive earth movements that bury villages and block rivers. The 2005 Kashmir earthquake in Pakistan triggered thousands of landslides, including one that created a temporary dam on a river, leading to a secondary flood disaster weeks later. Landslides can be deadly in their own right and often hinder rescue operations after the main earthquake, compounding the crisis for affected communities. Seismic waves travel in different forms, primarily P waves and S waves. P waves, or primary waves, are the fastest and move in a push-pull motion, while S waves, or secondary waves, are slower and move the ground up and down or side to side. The difference in arrival time between these waves allows early warning systems to detect a quake before the most damaging waves arrive. Some cities like Tokyo and Mexico City have advanced systems that can give residents several seconds to take cover, stop trains, and shut down gas lines, valuable seconds that can save lives. In ancient times, earthquakes were often attributed to the wrath of gods or mythical creatures. In Japanese mythology, a giant catfish named Namazu was believed to live beneath the earth and thrash about, causing earthquakes. In Greek mythology, Poseidon was the earth shaker, using his trident to create tremors. Even in modern times, some people interpret earthquakes as omens or punishments, although science has replaced superstition in understanding their true causes. However, cultural beliefs about earthquakes still influence how societies prepare for and respond to seismic disasters. While modern science has made great strides in understanding earthquakes, precise prediction remains elusive. Earthquake prediction differs from forecasting. Prediction implies knowing exactly when and where a quake will strike, while forecasting deals with probabilities over time. Despite decades of research, no method has been universally accepted for accurate short-term prediction. Even attempts using electromagnetic signals, animal behavior, or gas emissions have yielded inconsistent results. Scientists continue to work toward prediction models, but until then, early warning systems and earthquake-resistant infrastructure remain the most reliable forms of defense. The Earth's crust is not a single solid shell, but rather a mosaic of tectonic plates that float atop the semi-fluid mantle. The boundaries where these plates interact are the source of most earthquakes. There are three main types of plate boundaries: convergent, where plates collide; divergent, where they move apart; and transform, where they slide past one another. Each boundary type produces different styles of earthquakes. The infamous San Andreas Fault is a transform boundary, while the Himalayas were formed at a convergent boundary, where India collides with Asia. Understanding these boundaries helps geologists identify high-risk regions. Certain cities are surprisingly vulnerable to earthquakes due to their underlying geology. Mexico City, for example, is built on an ancient lakebed composed of soft sediments. These sediments amplify seismic waves, making quakes more intense than in surrounding areas. In the 1985 earthquake, buildings over 5 stories tall were hit hardest due to resonance with the ground motion. This phenomenon, called site amplification, shows that not just magnitude but also local soil conditions determine how destructive an earthquake can be. Urban planning in such areas must take these unique geologic traits into account to reduce future disaster impacts. Tsunamis caused by underwater earthquakes can travel across entire ocean basins at jetliner speeds, up to 800 kilometers per hour. In deep water, they may be barely noticeable, rising only a few centimeters above sea level. But as they approach shallower coastal waters, their speed decreases, and their height can increase dramatically, forming walls of water that devastate coastlines. The 2011 tsunami in Japan reached heights of over 40 meters in some places and moved several kilometers inland. Tsunami warning systems now use seismic data and underwater pressure sensors to issue alerts in minutes, saving countless lives in coastal areas. In addition to earthquakes on Earth, scientists have detected Marsquakes on Mars. NASA's InSight lander, deployed in 2018, recorded hundreds of seismic events on the red planet, many of which suggest that Mars is still geologically active. Unlike Earth, Mars has no tectonic plates. Its quakes likely originate from cooling and contraction of the planet's interior or from fault activity in its crust. Studying Mars quakes helps scientists understand the structure and history of other planets, providing insight into how rocky worlds evolve over billions of years, even in the absence of plate tectonics like we see on Earth. Before the invention of seismographs, earthquakes were dated and measured using historical records, geological evidence, and oral traditions. Paleoseismology is the study of ancient earthquakes through trenches dug across fault lines. By analyzing sediment layers and fault displacements, scientists can uncover evidence of prehistoric quakes and estimate how frequently large events occur in specific regions. This data is essential for understanding long-term seismic risks. For example, studies of the Cascadia subduction zone along the Pacific Northwest have revealed a history of massive quakes every 300 to 600 years, information that has drastically changed preparedness plans in that region. During the 1906 San Francisco earthquake, not only did the shaking cause massive destruction, but the fires that followed became the real catastrophe. Gas lines ruptured, and with water mains broken, fire crews had no water to douse the flames. The fires burned for days, destroying over 80% of the city and killing an estimated 3,000 people. In many large earthquakes, fire becomes a secondary yet devastating hazard. This historical lesson has led to modern infrastructure that includes automated gas shutoff valves and better emergency water systems to prevent similar disasters from occurring again. Earthquake magnitude and intensity are not the same. Magnitude refers to the amount of energy released at the earthquake source and is measured on scales like the moment magnitude scale (MW), which has largely replaced the older Richter scale. Intensity, however, measures the quake's effects on people, structures, and the Earth's surface, often using the modified Mercalli intensity (MMI) scale. A single quake can have one magnitude but multiple intensities across different locations. Understanding both helps seismologists assess how destructive an earthquake really was and how far its effects were felt. The Earth's internal structure plays a major role in how seismic waves travel. These waves can reflect, refract, and even get absorbed by layers of rock, magma, or mineral deposits. By analyzing how seismic waves change as they pass through the Earth, scientists can create models of the planet's interior, including the molten outer core and solid inner core. This technique, called seismic tomography, is like an ultrasound for the Earth. It's one of the few ways we can study what lies thousands of kilometers beneath our feet without ever drilling into it. Some of the most damaging earthquakes in U.S. history didn't happen in California, but in the central United States. In 1811 and 1812, a series of powerful quakes struck near New Madrid, Missouri. These events were so intense they reportedly caused the Mississippi River to flow backward temporarily and were felt as far away as Boston. Because the central U.S. has more rigid, old crust, seismic waves travel much farther than in California, where the crust is younger and more fragmented. Today, this region remains seismically active, and scientists continue to monitor it for signs of future large quakes. In 2001, an earthquake in Gujarat, India, registered a magnitude of 7.7 and caused the deaths of over 20,000 people, injuring more than 167,000 and leaving hundreds of thousands homeless. The quake hit on India's Republic Day, a national holiday, leading to widespread panic. What made the disaster more tragic was the failure of many buildings that were not earthquake-resistant, even though the area had known seismic risks. This disaster led to major reforms in India's building codes and public awareness campaigns about seismic safety, especially in vulnerable urban areas. Japan is one of the best prepared countries in the world when it comes to earthquakes, thanks in part to its education system. From a young age, children participate in earthquake drills, learn how to respond during emergencies, and are taught how to pack and maintain emergency kits. Japanese homes and workplaces often keep earthquake bags stocked with food, water, flashlights, and medical supplies. Japan's commitment to earthquake readiness, including infrastructure, public training, and early warning systems, has saved countless lives during major seismic events. This approach is now studied and adopted in many other earthquake-prone countries. The Andes Mountains in South America are a direct result of massive seismic activity caused by the subduction of the oceanic Nazca Plate beneath the South American plate. This collision zone generates frequent powerful earthquakes and has uplifted the Andes to some of the highest altitudes on Earth. As the plates continue to interact, the mountains grow taller by millimeters each year. While the majestic peaks attract tourists and mountaineers, they also pose a constant risk of earthquakes, landslides, and volcanic eruptions. The geological power that created these beautiful landscapes also makes them some of the most dangerous regions on the planet. Certain unusual atmospheric and environmental phenomena have been linked anecdotally to earthquakes, including glowing skies, strange animal behavior, and changes in groundwater levels. In some cases, people have reported seeing multicolored flashes in the sky moments before a major quake. Though often dismissed as folklore, some scientists believe these reports might be tied to piezoelectric effects, where rocks under stress release electrical charges, or even electromagnetic disturbances. While still under scientific investigation, these rare signs are sometimes referred to as earthquake precursors and continue to intrigue both researchers and eyewitnesses. Seismographs are highly sensitive instruments that can detect ground motion from earthquakes occurring thousands of miles away. In fact, the global network of seismometers is so refined that it can even register the vibrations caused by nuclear tests or large explosions. These instruments use a suspended mass and a recording system to track how the ground moves relative to the mass. Modern digital seismographs are now essential tools not only for earthquake detection, but also for tsunami warnings, volcanic activity monitoring, and even structural engineering research. Their data helps build safer cities and alert people to oncoming disasters in real time. The moment magnitude scale, which replaced the Richter scale, measures the total energy released by an earthquake and is more accurate for very large seismic events. Unlike the Richter scale, which saturates at high magnitudes, the moment magnitude scale can measure the size of megathrust earthquakes more precisely. It calculates magnitude based on the seismic moment, the product of the fault area, the average slip on the fault, and the rigidity of the rocks involved. This makes it the global standard used by seismologists today and allows for consistent comparisons of earthquakes around the world. Earthquakes can sometimes cause seiches, standing waves in enclosed or semi-enclosed bodies of water, like lakes, swimming pools, or harbors. These waves slosh back and forth, sometimes hours after a quake, and can reach surprising heights. In 1955, a seiche caused by a distant earthquake in Alaska was observed in Norway's fjords. Even swimming pools far from an epicenter have been known to spill dramatically during seismic events. These water oscillations, though often harmless, are a striking visual reminder of how far and wide an earthquake's energy can travel. Soil composition can dramatically affect earthquake damage. Areas built on soft clay or loose sand tend to amplify seismic waves, increasing shaking intensity. This phenomenon, known as side effect or soil amplification, explains why some neighborhoods suffer greater damage than others during the same earthquake. Mexico City, Kathmandu, and parts of San Francisco are particularly vulnerable due to the types of soil and sediment they sit on. Engineers now conduct detailed geotechnical studies before constructing buildings in such areas to design foundations that can withstand these unique seismic challenges. The 2010 earthquake in Haiti had a magnitude of 7.0 but caused over 300,000 deaths and massive destruction, largely due to poor construction standards, high population density, and lack of emergency response infrastructure. The capital, Port-au-Prince, was hit especially hard, with thousands of buildings collapsing, including hospitals, schools, and government offices. The disaster highlighted the critical importance of building codes, urban planning, and international cooperation in post-disaster recovery. It also served as a wake-up call for many developing nations with similar vulnerabilities. Earthquakes can create permanent changes to the Earth's surface, such as vertical uplift, horizontal shifts, and even ground ruptures that split roads, pipelines, and rivers. The 1906 San Francisco earthquake resulted in a surface rupture that stretched more than 300 miles along the San Andreas Fault, with horizontal displacement of up to 20 feet in some areas. These changes are recorded and studied by geologists to understand fault movement and stress release. The visible scars left behind become natural laboratories that provide invaluable insight into the dynamics of Earth's shifting plates. Earthquake-resistant architecture has become a specialized field of study, especially in countries with high seismic activity. Engineers now use computer simulations to model how buildings will respond to different quake scenarios, allowing them to tweak designs for better performance. Innovations such as shock-absorbing foundations, reinforced concrete cores, cross-bracing, and flexible materials have made modern structures much more resilient. Countries like Japan, New Zealand, and Chile lead in implementing these technologies, often requiring them by law in urban construction. These advancements have significantly reduced casualties and property loss in earthquakes that would have been catastrophic just a few decades ago. The Nazca Plate, located off the western coast of South America, is slowly sliding beneath the South American plate in a process called subduction. This movement not only created the Andes Mountains, but also generates intense seismic activity along the Peru-Chile Trench. These subduction zone earthquakes are some of the strongest on Earth, often exceeding magnitude 8.0. They can also trigger tsunamis and volcanic eruptions. Countries along this boundary, such as Peru, Ecuador, and Chile, have had to develop extensive monitoring and emergency systems. The geological violence of this plate boundary is a key driver of the continent's evolving landscape and seismic risk. The 1994 Northridge earthquake in California caused unexpected levels of destruction, not only due to its strength but also because of its unusual fault behavior. The quake occurred on a blind thrust fault, a type of fault that doesn't reach the Earth's surface, making it invisible to traditional surface mapping techniques. It struck a densely populated region of Los Angeles, causing over $20 billion in damage. The event was a wake-up call for engineers and geologists alike, proving that many dangerous faults remain hidden underground. It led to significant updates in building codes and a renewed focus on identifying unseen threats. Earthquakes can drastically alter groundwater systems. When the Earth's crust shifts, underground aquifers may collapse, drain, or suddenly fill with water. In some cases, wells dry up or become muddy, while in others, new springs emerge. After the 1989 Loma Prieta earthquake in California, residents reported sudden changes in well water quality and flow rates. Geologists study these changes to learn more about subsurface geology and the interaction between seismic forces and groundwater. These effects also raise concerns for communities that depend on groundwater for agriculture and drinking water, as supply changes can be sudden and unpredictable. In some extreme earthquakes, the shaking has caused rivers to reverse course, at least temporarily. During the 1811 New Madrid earthquake, eyewitnesses reported that parts of the Mississippi River actually flowed backward for several hours due to ground uplift and seismic waves displacing massive volumes of water. This phenomenon, though rare, demonstrates the sheer force of tectonic movement during major quakes. River reversals can cause flooding, alter navigation routes, and destroy nearby ecosystems. These dramatic geological shifts are studied using historical records, satellite imagery, and post-event riverbed surveys to better understand how large earthquakes shape surface water systems. Though often associated with the West Coast, the central and eastern United States are not immune to earthquakes. The eastern U.S. has older, colder, and more rigid crust, which allows seismic waves to travel farther. A moderate earthquake in Virginia in 2011 was felt in over a dozen states and even caused evacuations in Washington, D.C. While large quakes are less common east of the Rockies, they are still possible and potentially more widespread in effect. This has led to increased efforts to update building codes and emergency plans, even in places not traditionally seen as earthquake hotspots. Earthquake Early Warning Systems, EWS, are one of the most promising tools in reducing injury and damage. These systems detect the fast-moving but less destructive P waves that arrive before the more damaging S waves. With just a few seconds' notice, subways can stop, elevators can open at the next floor, surgeons can pause procedures, and people can take cover. Japan's nationwide EWS has been credited with saving lives in several major quakes. In recent years, similar systems have been implemented or tested in California, Mexico, and Taiwan. While not a prediction tool, the EWS provide vital seconds that can make a major difference. In high seismic zones, critical infrastructure such as hospitals, fire stations, and schools are often built to higher seismic standards than regular buildings. These structures are expected to remain functional during and after a quake, making them lifelines during emergencies. Retrofitting older buildings to meet these standards is a costly but essential task, especially in cities with aging infrastructure. Chile, for example, requires public hospitals to be earthquake-resistant and self-sustaining for several days. These investments help ensure that emergency services can function even when cities are otherwise paralyzed by disaster, significantly improving survival and recovery rates. In the wake of a major earthquake, looting, misinformation, and public panic can become as dangerous as the quake itself. Social media and unverified messaging apps can rapidly spread rumors, such as false tsunami warnings or reports of additional quakes, leading to chaos. Emergency management agencies now incorporate social media monitoring and public communication strategies to dispel rumors and provide accurate information quickly. Training the public on how to access verified information has become an integral part of disaster preparedness in the digital age, helping communities maintain calm and coordinate better during crises. The concept of seismic gaps plays a key role in earthquake forecasting. A seismic gap is a segment of a fault that has not ruptured in a long time, even though neighboring segments have. This suggests that stress is accumulating and that the area is likely to experience a large earthquake in the future. One well-known seismic gap is in the Cascadia subduction zone off the Pacific Northwest coast of the US and Canada. The absence of recent quakes in this area, combined with geological evidence of past megaquakes, has led scientists to warn of a potential catastrophe that could rival or exceed the 2011 Japan disaster. The Cascadia subduction zone, located off the Pacific Northwest coast of the United States and Canada, is one of the most dangerous seismic regions in the world. This fault has produced massive earthquakes every 300 to 600 years, and the last one occurred in 1700. Scientists estimate the next megathrust quake could reach magnitude 9.0 or higher, unleashing tsunamis and widespread destruction from Northern California to British Columbia. This looming threat has spurred comprehensive emergency planning, earthquake drills, and retrofitting of critical infrastructure in cities like Seattle, Portland, and Vancouver to prepare for a disaster that could strike at any time. Earthquakes are not limited to our planet. They also occur on the moon, where they are called moonquakes. Apollo astronauts first placed seismometers on the lunar surface in the 1970s, and these devices recorded hundreds of quakes caused by tidal forces from Earth, thermal expansion of the moon's crust, and occasional meteorite impacts. Unlike earthquakes, moonquakes can last up to 10 minutes because the moon's dry, rigid crust transmits seismic energy more efficiently. This discovery has influenced future lunar missions, as moonquakes must be considered when planning habitats and infrastructure for long-term stays on the moon. Liquefaction, a dangerous side effect of earthquakes, can devastate entire neighborhoods when loose, water-saturated soil loses its strength and behaves like a fluid. Buildings and roads can sink, tilt, or collapse without warning. The 1989 Loma Prieta earthquake in California caused severe liquefaction in the Marina district of San Francisco, leading to building collapses and fires. Scientists now use ground-penetrating radar and soil sampling to identify areas at risk for liquefaction, helping city planners mitigate future disasters. Despite these precautions, liquefaction remains one of the most destructive and least predictable earthquake-related hazards. The phenomenon of earthquake lights continues to baffle scientists. These mysterious flashes of light, which can appear as glowing orbs or flickering flames in the sky, are sometimes reported before or during earthquakes. Possible explanations include electrical discharges from stressed rocks or static electricity generated by the rapid movement of tectonic plates. While rare, credible sightings and video evidence from recent earthquakes have sparked renewed interest in studying these unusual events. If understood better, earthquake lights might one day help seismologists identify warning signs before major quakes strike. Large earthquakes can change the flow of underground magma and even trigger volcanic eruptions. The 1960 Valdivia earthquake in Chile, the most powerful in recorded history at magnitude 9.5, destabilized several volcanoes in the Andes. Similar effects have been observed in Alaska, Indonesia, and Japan. While not every quake leads to eruptions, seismic waves can fracture rock, alter pressure in magma chambers, and create new pathways for molten rock to rise. Volcanologists closely monitor active volcanoes after major earthquakes to detect any signs of heightened activity, knowing the two natural hazards are often interconnected. The 1755 Lisbon earthquake was one of the deadliest and most culturally influential earthquakes in European history. Estimated at magnitude 8.5 to 9.0, it triggered fires and tsunamis that killed tens of thousands of people. The disaster shocked Enlightenment-era Europe and spurred philosophical debates about the nature of suffering and divine punishment. It also led to advances in earthquake engineering and scientific study, as Portugal's Prime Minister Sebastião de Mello ordered detailed surveys of damage patterns. The lessons learned from Lisbon's devastation laid the foundation for modern seismology and disaster planning in Europe. Micro-earthquakes, small quakes with magnitudes less than 2.0, happen thousands of times each day around the world but are rarely felt by humans. While they cause no damage, they play an important role in releasing tectonic stress gradually. Some scientists believe that swarms of micro-earthquakes can precede larger seismic events, although this is not always the case. Networks of sensitive seismometers monitor these tiny tremors, as patterns in their frequency and location may provide valuable clues about the condition of faults and the likelihood of larger earthquakes in the near future. Earthquakes can displace massive amounts of water in lakes and fjords, creating waves called seiches. These standing waves can slosh back and forth for hours or days, sometimes causing unexpected flooding far from the epicenter. After the 2011 Tohoku earthquake in Japan, seiches were observed in lakes as far away as Norway. Although generally less destructive than tsunamis, seiches can damage shorelines, boats, and infrastructure. Their occurrence highlights how the effects of an earthquake can ripple across the globe, reaching places thousands of kilometers away from the origin of the seismic activity. The 1970 Ancash earthquake in Peru caused one of the deadliest landslides in history. The magnitude 7.9 quake destabilized Mount Huascaran, sending a massive chunk of ice, rock, and mud down the mountainside at 200 kilometers per hour. The landslide buried the town of Yungay, killing approximately 70,000 people. This tragedy underscores how earthquakes often trigger secondary disasters such as landslides, floods, and avalanches, which can cause even more destruction than the initial shaking. Today, hazard maps and monitoring systems are used in mountainous regions to reduce the risk of earthquake-induced landslides. One of the most important tools in earthquake studies is GPS technology. By tracking the slow movement of tectonic plates with millimeter precision, scientists can identify which regions are accumulating stress. This data helps refine seismic hazard maps and can even estimate how much strain has built up on specific faults. In Japan and California, dense GPS networks provide real-time measurements of crustal deformation, feeding information directly into early warning systems. This use of GPS has revolutionized earthquake science, offering a clearer picture of where the next big rupture might occur. Earthquake risk isn't fixed. It can be reduced dramatically with ground improvement methods that combat hazards like liquefaction. Engineers densify loose sands with vibrocompaction, mix cement into weak soils to create stiff columns, or install gravel drains and wick drains so excess poor water pressure dissipates during shaking. Pile foundations can transfer loads to deeper, stronger layers, while mat slabs spread demand more evenly at the surface. These treatments aren't one-size-fits-all. They're chosen after geotechnical investigations, site response analyses, and cost-benefit studies. But when applied correctly, they keep buildings upright on soil that might otherwise behave like quicksand. Public guidance during shaking has been refined through decades of injury data and structural analysis, leading to the simple message: drop, cover, and hold on. The goal is to prevent falls, shield the head and neck from falling debris, and stay put until violent motion passes. Common myths persist, like standing in a doorway or running down stairs, which often increases risk. Equally controversial internet tips, such as the so-called triangle of life, have been widely criticized by safety agencies. The consensus is clear: get low, get under a sturdy table or desk if possible, protect yourself, and hold on until the shaking stops. Unreinforced masonry is one of the most dangerous building types in earthquakes because brick and mortar are strong in compression but brittle in tension and shear. Retrofit strategies include adding steel frames, installing shotcrete or fiber-reinforced polymer overlays, tying parapets and facades back to diaphragms, and anchoring walls to floors and roofs. Soft storywood apartments with weak ground-level parking bays are another notorious risk. Retrofits add moment frames, shear walls, or steel columns to stiffen the first story. Non-ductile concrete buildings, common for mid-century construction, often require column jacketing and diaphragm strengthening to prevent catastrophic brittle failure. Critical lifelines determine whether a city can function after a quake. Bridges, water and wastewater systems, power grids, gas lines, and telecom networks. Engineers use flexible couplings on pipelines to tolerate joint movement, seismic shutoff valves to stop gas-fed fires, and base isolation or dampers on essential bridges. Substations are braced, transformers anchored, and control rooms equipped with racks mounted to withstand lateral loads. Because systems are interdependent, a broken water main can disable firefighting. Utilities run scenario drills, stage spare parts, and design for rapid segment isolation so damage is contained and service can be restored in hours instead of weeks. Crowdsourced data has transformed seismology. Programs like Did You Feel It? Collect public reports of shaking, mapping intensity within minutes and filling gaps between sparse instruments. Low-cost sensors such as Raspberry Shake units extend networks into schools and homes, while smartphones can detect motion and, when aggregated, help confirm events. These macroseismic observations complement high-end seismometer arrays by revealing how shaking varies neighborhood to neighborhood. The result is faster situational awareness for emergency managers, improved shaking models for engineers, and a powerful way to engage communities in the science that ultimately helps protect them. For businesses, earthquakes are as much an economic shock as a physical one, and continuity planning determines survival. Firms that prearrange remote work options, off-site data backups, alternate suppliers, and manual workarounds for power or internet outages rebound faster. Securing racking, anchoring heavy equipment, and bracing sprinklers prevents both injuries and ruinous inventory losses. Cash flow buffers, parametric insurance, and mutual aid agreements with nearby partners further reduce downtime. After major quakes, studies often show that preparedness measures costing a fraction of annual revenue can make the difference between reopening in weeks or closing permanently. Protecting cultural heritage from earthquakes requires blending conservation with modern engineering. Museums anchor display cases and art racks, install non-slip mounts for artifacts, and use isolation pads that decouple delicate objects from building motion. Historic structures can be discreetly strengthened with steel ties, fiber-reinforced polymers, or even base isolation inserted beneath floors while preserving original facades. Detailed laser scans and digital twins document pre-retrofit conditions and guide reversible interventions. When heritage is seismically resilient, communities retain not only their safety, but also the symbols of identity that help them emotionally recover after disaster. Urban planners in seismic regions design cities with evacuation, firefighting, and shelter in mind. Wide, obstruction-free corridors and open spaces double as assembly areas and helicopter landing zones. Wayfinding signage and illuminated maps guide residents, even if power fails. Neighborhood disaster hubs stock water, sanitation supplies, radios, and first aid, while codes limit flammable cladding and require fire breaks to control post-quake blazes. Microzoning maps steer dense development away from landslide-prone slopes and deep soft soils. Resilient cities aren't just shaped by strong buildings. They're stitched together by routes, resources, and rules that work when everything else doesn't. At the heart of earthquake physics is friction on faults, which alternates between sticking and slipping as stress builds and releases. Laboratory experiments with granite blocks and high-speed sliders reveal rate-and-state behavior. Friction changes with slip speed and contact history, sometimes enabling slow creep and other times runaway rupture. In large events, rupture fronts can outrun shear wave speeds, producing super shear shocks that intensify shaking in a narrow Mach cone. These insights feed into numerical rupture simulations that help engineers anticipate pulse-like ground motions capable of delivering brief but extremely damaging velocity spikes to structures. Coastal earthquake preparedness increasingly emphasizes vertical evacuation for tsunamis when horizontal escape to high ground is impossible. Specially designed towers, berms, and reinforced roofs are engineered to resist hydrodynamic forces and debris impact, with stairways sized for rapid crowd flow and platforms stocked with supplies. Evacuation maps show walking times from schools and neighborhoods, and drills teach residents to move immediately after strong or long shaking, without waiting for sirens, because locally generated tsunamis can arrive in minutes. These structures turn flat coastlines into life-saving high points when every second counts. Earthquake swarms are sequences of numerous small to moderate earthquakes occurring in a localized area over days, weeks, or even months, without a single large main shock. These swarms often baffle scientists because they don't follow the typical foreshock main shock aftershock pattern. Some are linked to volcanic or geothermal activity, like those around Yellowstone or Iceland, while others happen in intraplate settings without clear causes. Though usually non-destructive, swarms can raise alarm due to their persistence and frequency. Seismologists monitor them closely because, on rare occasions, a swarm might transition into a larger, damaging quake, though predicting which will is still a major challenge. The term silent earthquakes refers to slow slip events, fault movements that release strain over days or weeks instead of seconds, producing little or no shaking. Detected by high-resolution GPS rather than seismometers, these quakes were first discovered in subduction zones like Cascadia and Japan. Though silent, they are far from harmless. They transfer stress along faults and may load locked segments that eventually rupture in massive earthquakes. Scientists now study slow slip events to understand stress evolution along faults and how they might serve as precursors to larger seismic disasters. Their discovery has revolutionized how geologists view tectonic strain accumulation. Deep beneath Earth's surface, massive slabs of the crust, known as tectonic plates, sink into the mantle in subduction zones, producing intense pressure and heat. This creates a type of deep earthquake known as an intraslab quake, often occurring 300 to 700 kilometers below ground. Despite their depth, these earthquakes can be felt at the surface due to their enormous energy. The 2013 Sea of Okhotsk quake, over 600 kilometers deep, was felt across Russia and even in Tokyo. These quakes reveal much about Earth's interior and plate recycling processes, making them a subject of major scientific interest. When large earthquakes strike, they can permanently deform the Earth's crust, moving entire regions by several meters. Satellite radar imagery and GPS data have shown how ground can shift horizontally or vertically, sometimes by as much as 10 meters. The 2011 Tohoku earthquake moved parts of Japan's main island eastward by over 2.5 meters and caused a measurable drop in elevation along the coast. These shifts can alter river courses, change coastlines, and impact infrastructure planning. In extreme cases, such deformation is visible in before and after aerial imagery, revealing the awesome power of tectonic forces at work in real time. Certain animals appear to sense earthquakes before they happen, though the scientific community remains divided on whether this is due to real precursors or coincidence. Reports include dogs howling, cats fleeing, toads abandoning ponds, and zoo animals acting erratically hours or days before quakes. One theory suggests animals may detect subtle ground vibrations, electromagnetic changes, or gas emissions that precede seismic activity. Despite extensive anecdotal evidence, attempts to use animal behavior as a reliable early warning system have not yet succeeded. However, the topic remains a fascinating intersection of biology and geophysics that continues to draw research interest. Ancient civilizations often attributed earthquakes to gods, mythical creatures, or supernatural causes. In Japan, a giant catfish named Namazu was believed to cause quakes when it thrashed beneath the earth. In Greek mythology, Poseidon, god of the sea, was also called the Earthshaker and was thought to create earthquakes by striking the ground with his trident. The Incas believed their earth goddess Pachamama could cause tremors when disrespected. These myths, while unscientific, reflected cultural understandings of natural disasters and shaped early responses to seismic events. Many of these stories persist today as symbolic explanations in folklore and religious tradition. While most earthquakes are natural, humans have also caused seismic activity, known as induced earthquakes. These events result from mining operations, reservoir-induced pressure changes, oil and gas extraction, and especially wastewater injection and hydraulic fracturing, fracking. In Oklahoma, earthquake frequencies surged in the 2010s due to deep injection wells, with several damaging quakes occurring in previously quiet areas. Induced earthquakes are typically smaller than tectonic ones but can still cause damage and raise legal and regulatory concerns. As energy development continues, scientists and policymakers are working to understand, monitor, and mitigate human-triggered seismicity around the world. The deadliest earthquake in recorded history struck Shaanxi, China, in 1556, killing an estimated 830,000 people. Known as the Jiaojing earthquake, it occurred in a region where many people lived in artificial caves carved into soft, lush hillsides, which collapsed en masse during the quake. The disaster reshaped the local geography and history. Records from the time describe massive ground fissures, landslides, and entire towns destroyed. Despite lacking modern measuring tools, ancient Chinese scholars documented the event in detail, allowing today's seismologists to study its causes and effects. It remains a grim reminder of how vulnerable human settlements can be to seismic events. In some rare earthquakes, the rupture propagates in unusual or unexpected directions, causing asymmetric ground shaking. The 2010 Mal earthquake in Chile and the 2015 Gorkha earthquake in Nepal both showed unilateral rupture propagation, where most of the slip travels in one direction along the fault. This produces intense shaking on one side of the fault and weaker motion on the other, affecting damage patterns. Understanding rupture direction helps improve seismic hazard maps and building codes, especially in urban centers located on just one side of an active fault. Engineers and seismologists use this data to simulate worst-case scenarios more accurately. The energy released by a magnitude 9.0 earthquake is equivalent to over 475 million tons of TNT, or nearly 32,000 Hiroshima atomic bombs. Despite this, the Richter scale is logarithmic, so a magnitude 9.0 earthquake isn't just a bit stronger than an 8.0, it's actually 32 times more powerful in terms of energy release. This exponential increase explains why each whole number jump on the scale corresponds to vastly more destructive potential. Understanding the energy scale is crucial for public awareness, as many people mistakenly assume that a 6.0 and a 7.0 quake differ only slightly, when in reality the difference can be catastrophic.